Hello, this is Jack Jackson. Today we're going to be talking about sets, several things that relate to them, so operations on them, and intervals, which are a particular kind of set. So some of the things we're going to be doing here are talking about the basic definitions and notations of sets, how to write down sets as lists with braces, set builder notation. We'll talk about elements and subsets. Then we'll talk about some set operations of intersection, union, and complement. And we'll use Venn diagrams to represent this information. And we're going to talk about interval notation for intervals of real numbers. Sets are collections. Think of having a container with some things in it. The things inside a set can be anything. Often there'll be numbers for this class, but we can do other sets too. Sets of physical objects, people, measurements, letters, geometric figures, ordered pairs of numbers, other sets. Anything could be inside these sets. The things in the set are called the elements of the set. So a set is a collection of elements. We must be able to determine if something is either an element of the set or it is not an element of the set. So a potential element is not in a set multiple times. Either it's in the set or it's not in the set. We may represent sets in many ways, but there are some standard symbols associated with set notation. So to begin with, we'll talk about these little curly braces to represent the container holding the elements. And if the list is fairly small, then all we have to do is simply list out the elements of the set between the braces, separated by commas. And we often name our sets with the capital letter. It doesn't have to be a capital letter. We can name them however we want, but it's often a capital letter. So we could say the set A equals the set containing the elements 1, 2, 3, and 4. Now the order that we list the elements in the set is totally irrelevant. There's no order inside the set. So the set containing 1, 2, 3, and 4 is the same set. It's absolutely equal to the same set as the set 1, 3, 4, 2. Now this little looks kind of like an E or an epsilon. This symbol is read is an element of. Often in mathematics we use a slash through a symbol to mean not. So like you're familiar with not equal to, not less than. So this symbol here with the slash through it means is not an element of. So we could say 1 is an element of the set containing 1, 2, 3, 4. But 8 is not an element of the set containing 1, 2, 3, 4. So with a simple list like that, it's very easy to see if something's an element or not an element. And of course, if you've got a small number of items, the best way you can describe a set is just to actually just list them out with this notation. However, often sets are very large or even infinite in size, and so we can't physically list them all out. Now, if we can write down enough of the list that there's a pattern to it that we think is very clear, then we can use these three little dots, ellipses, to continue the notation. So this funny looking N stands for the set of natural numbers, which is the set containing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, etc. going on forever. We can often be more precise, however, rather than trusting the reader to understand what pattern we're meaning when we make our list. We can be explicit about this pattern by providing some kind of rule that lets us know if something is an element of the set or not. Now look down here where it says E equals. So the set E equals, and I'll read this, the set of all elements of the form 2 times n such that n is an element of the set of natural numbers. Notice again that funny looking n is in the set of natural numbers. It says n is an element of the set of natural numbers. This vertical line is such that. Sometimes some people will use a colon here, 2 dots, instead of the vertical line. I'll use the vertical line. So this is saying we can let n be any natural number, 1, 2, 3, 4, 5, 6, 7, etc. But what we have in our set is 2 times those natural numbers. So we have 2 times 1, which is 2. We have 2 times 2, which is 4. 2 times 3, which is 6. 2 times 4, which is 8, and so forth. So we get 2, 4, 6, 8, 10, 12, etc. Well, that's just the natural number multiples of 2, or we have another word for that. That's the even natural numbers. So an even number is just a multiple of 2. Alright, now it's your turn to do a little exercises here. I have 4 different exercises, 4 going one direction, 4 going the other direction. So the first 4, I give you the set builder notation and have you write it out as the little curly braces and list it out. In the second 4 exercises, it goes the other direction. I've given you the list or some other description for the set, and you need to write out the set builder notation. Now, as usual with these lectures, it's about time for you to pause this lecture and work this out. So you're going to hit your pause button, work this out carefully, and then come back and check your work. It's very important that you're working through these exercises, these lectures, that you do these exercises yourselves. Okay, you need to be an active participant in the learning. Okay, press pause now. Okay, well now you're back. Let's take a look at this and see if you came up with these answers. So let's look at the first one, the set of elements of the form n plus 3 such that n is an element of the natural numbers and n is less than 5. So this comma, when we have these condition on the right, is kind of like an and. You have to have both of these conditions satisfied. So our number n has to be a natural number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. But it also has to be less than 5. Well, that narrows it down to being just 1, 2, 3, and 4 for n. But it's not just n that we have in there. We have n plus 3. So we take 1 plus 3 is 4, so that's an element of our set. 2 plus 3, that's 5, that's another element. 3 plus 3 is 6, there's another element. And 4 plus 3 is 7, there's our last element of the set. So it's just the set containing 4, 5, 6, and 7. The next one is the set of all n such that n is an integer and the absolute value of n is less than 5. Well, that's the set -4, -3, -2, -1, 0, 1, 2, 3, and 4. So it has to be close to 0. How close? Within 5, less than 5. So 5 and -5 are not included. But also the stuff in between these things are not included either because it has to be an integer. Okay. Here's an example that has nothing to do with numbers. Set of all C such that C is a primary color. Well, that would be the set containing red, blue, and yellow. Now, remember when I said the comma here, once you get to the right of your such that, is kind of like an and. Well, the comma on the left here is kind of like an or. So the condition is n has to be a natural number and n is less than 6. Well, that narrows it down to 1, 2, 3, 4, 5 are the possibilities for n. And n is the thing, one of the things that's actually in the set. So one form the numbers have is just n. So we put in all those n's, 1, 2, 3, 4, 5. Okay, 6 is not less than 6, 7 is not less than 6. So we stop at 5. But then we also have another part of our set that looks like 10 times n. So we take all those n's and multiply them by 10. So that gives us 10, 20, 30, 40, 50. And so all 10 of these elements are actually the set. It's the set containing 1, 2, 3, 4, 5, 10, 20, 30, 40, 50. Again, you can list this in any order. I happen to list it in increasing order, but it's not really necessary. It's the same set if it's listed in a different order. Now let's write the sets in set builder notation. And some of these there might be an alternate way of writing it, the way I've done it. So we see that the first one is 3, 6, 9, 12, 15. Hopefully you saw a pattern there where these are just the multiples of 3. The first one's 3 times 1, the next one's 3 times 2, then 3 times 3, 3 times 4, 3 times 5. So they all have the form 3 times n, where n is a natural number. So it's a set of all numbers of the form 3 times n such that n is a natural number. It's the multiples of 3. Natural number multiples of 3. Now the set of odd integers. Okay, this is a little bit more work. If we just had n, that would be all integers. If we multiply by 2, that would give us the even integers, 2, 4, 6, 8. Okay? If we would add 1 to that, that would give us the odd integers. Okay, so notice it's one way to write this is the set of all numbers of the form 2n plus 1 such that n is an integer. Remember, I use that funny looking z for the integers. Now, notice that, well, let's just try some of these out. If n is 0, 2 times 0 plus 1 is 1. So that gives us the odd number 1 in our set. If n is 1, 2 times 1 is 2 plus 1 is 3. That gives us the odd number 3. If n is 2, 2 times 2 is 4 plus 1 is 5. So that gives us the odd integer 5, and so forth. Now let's try negative 1. Negative 1. 2 times negative 1 is negative 2 plus 1 is the odd integer negative 1. 2 times negative 2 is negative 4 plus 1 is negative 3. Again, an odd integer. And so that gives us a set of all odd integers in a set builder notation. Now, of course, if we had the set 5, 6, 7, 8, that's a real small set. It's easier to just describe that just like that. But we could use set builder notation if we wanted to. We could say the set of all n, such that n is a natural element of the natural numbers, and 4 is less than n, which is in turn less than 9. So the natural numbers between 4 and 9, not including the 4 and 9, just between. You could have also said it this way: the set of all n such that n is a natural number, and 5 is less than or equal to n, which is in turn less than or equal to 8, if you'd rather you do it that way. That way we do include the endpoints of 5 and 8. The next one, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, the set containing that, is equal to the set of all x such that x is a day of the week. Now, I've already used this in the last section and earlier in this video a little bit. Here are some symbols for some standard sets of numbers. They're all using a Blackboard boldface font, which is what you do for these particular sets. So the n is for the set of natural numbers, the set containing 1, 2, 3, 4, 5, 6, 7, 8, and so forth. W is the set of whole numbers, which is the same as the natural numbers, but it also has 0 in it. The set of integers has the set of whole numbers and their additive inverses, their opposites. So not only does it have 0, 1, 2, 3, 4, 5, etc., it also has negative 1, negative 2, negative 3, negative 4, negative 5, etc. So the two sets of 3 dots help us see that that goes on forever in both directions. Q for quotient, is the set of rational numbers. It's a set of all numbers of the form p over q such that p is an integer, q is an element of the integers but not 0. This turns out to be the same as the set of repeating or terminating decimals. R, the set of real numbers, is the set of all decimal numbers. I, the set of imaginary numbers, is a set of numbers of the form bi, such that b is a real number but not 0, and I is the principal square root of negative 1. C is the set of complex numbers, which is the set of all numbers of the form a plus bi, such that a and b are real numbers, and again I is the principal square root of negative 1. So we talked about these quite a bit in our last unit, our last section of this unit. One special set is a container only containing no elements at all. This set with no elements is called the empty set or null set, and is denoted either with the braces and just nothing in the middle, or with this kind of circle with a slash through it for the null set or empty set. Now, the next thing we want to talk about is the concept of a subset. We can think of taking a container and scooping out some, or perhaps none, or perhaps all, of the elements of a set. The resulting set that we get is a subset of the original set. And so we have the following definition and notation. We say A is a subset of B, and use this notation. A is a subset of B. By the way, it's not because I can't spell if. IFF stands for if and only if. So A is a subset of B if and only if every time X is an element of A, then X has to be an element of B. X an element of A implies X is an element of B. So everything that's inside A has to also be inside B. B could have some stuff that's not in A, but A can't have anything that's not in B. Note that any subset, or any set, is a subset of itself. So for any set A is a subset of A. Every set is a subset of itself. That's kind of what the little line at the bottom kind of indicates, that it allows the equality. The empty set is a subset of any set. So for any set A, the empty set is a subset of A. So let's think of, you just scoop down but you don't get anything. So that's a subset. We say A is a proper subset of a set B if and only if A is a subset of B and A is not equal to B. And my little slash got off here. So this slash should be underneath like it is down here. Should be going through the equal to part. So A is a proper subset of B if and only if A is a subset of B and A is not equal to B. Now, some people use a notation with the subset symbol without the little line underneath. And the problem with that is it's not consistent use everywhere. Some people use that symbol to mean what I'm saying, just a subset, allowing equality. And other people use that symbol for a proper subset, not allowing inequality. Because that, I think, is confusing, we will not use this symbol, just A, with this sort of symbol here, looks like a subset symbol, but without the line underneath. We will not use that notation. We'll use the subset with the equal under, with the line under, if equals is a possibility, and we'll have a slash through the little equal part if it's not a possibility for equals. The power set is the set of all subsets. So the power set of A, with this kind of script P and an A, is the set of all subsets of A. So, for example, if the power set of the set 1, 2, 3 is itself a set, and the elements of this set are themselves sets. Well, you always have the empty set, and you always have the set itself being subsets, but we have others here. We have the set of size 0, the empty set, the sets of size 1, the set containing 1, the set containing 2, and the set containing 3 are elements of the power set. And then we have the sets of size 2, the set containing 1 and 2, the set containing 1 and 3, and the set containing 2 and 3, as well as the set of size 3, the set containing 1, 2, and 3. So this is the set of all subsets of A, which is the power set of A. Alright, so let's look at some examples involving elements and subsets. So everything on this page, hopefully, is a true statement. So let's look at them. So the first one, we would say the set containing 1 and 2 is a subset of the set containing 1, 2, 3, 4. Okay? But we would say the set containing 2 and 5 is not a subset of the set containing 1, 2, 3, and 4. Notice the big slash through again means not. Why is this one not? Doesn't work? Well, it's because 5 is not an element of the set 1, 2, 3, 4. 2 is not a subset of the set containing 1, 2, 3, 4. 2 is not a set. It's a number, it's not a set. So it can't be a subset of anything. 2 is an element, however, of the set 1, 2, 3, 4. And the set containing 2 is a subset of the set containing 1, 2, 3, 4. So in other words, to be a set, it needs the container. And so we have a container containing 2. That is a subset of the container containing 1, 2, 3, 4. 2 by itself, without the container, is an element of the set 1, 2, 3, 4. Okay, look at the next one. Get a little bit trickier here. The set containing 2, 3 is not a subset of the set containing the ordered pair 2, 4, 3, 5, and 4, 8. Notice that this set here has 3 elements, and each element is an ordered pair. So the elements are not numbers, the elements are ordered pairs of numbers. So notice that the ordered pair 2, 4 is an element of that set. It's not a subset, it's an element of that set. Okay, go on to the next column. The set containing 1 and 2 is not a subset of the set containing the set 1 and 2 and the numbers 3 and 4. So the set on the right has 3 elements. One is 3, a number. One is another number, 4. And the other one is not a number at all. It's a set which itself contains two numbers. So in this case, the set 1, 2 is actually an element of the set on the right, the set containing the set 1, 2, and the elements 3 and 4. So if you think of this as a big box, the thing on the right is a box, and you'll see in that box a 3 and a 4 and another box, and that other box has 1 and 2 in it. Okay, but the set 3, 4 is a subset of that set, the set containing 1, 2, and 3, 4, because you could reach in and scoop out the 3 and the 4 and make a new box that contains just the 3 and the 4. Every element in the set 3, 4 is an element in the set on the right. Now here's one that's always interesting. Is the set containing the empty set empty? Well, no. Because what do you have? That's like saying, is a box containing an empty box empty? No. The outside box has something in it, an empty box. So it has a box in it. And so the set containing an empty set is not itself empty. It has an element. The empty set is an element of that set. And of course the empty set is a subset of every set, so the empty set is a subset of the set containing the empty set. It's a subset of every set. Last couple of those got a little bit interesting, so you may want to think about those a few minutes before you go on. When you're ready, if you need to, press pause, but if you're ready, let's go on. So here I have 6 statements. These are true or false statements. So classify each one as true or false. And if it's false, tell me what went wrong. Why is it false? So let's go ahead and do this one and come back when you're finished. Press pause now. Okay. The set containing 0, 1, and 2 is a subset of the natural numbers. Well, that's false because the set on the left, that's supposed to be the subset, contains the element 0, but the set on the right does not contain 0. 0 is not an element of the natural numbers, so that is not a subset. We could fix it by either throwing 0 out of the set on the left or by increasing the set on the right to the whole numbers. Number 2, the set containing -2, 6, -11, 5 is a subset of the integers. True. Every element in the set on the left is also an element of the set on the right. So that is true. Notice it doesn't matter what order we list them in. This time I did not list them in increasing order. The next statement is true. It's actually a series of a whole bunch of statements, but this shows you relationship among these basic sets of numbers. The natural numbers are a subset of the whole numbers, actually a proper subset. The whole numbers are a subset of the integers. The integers are a subset of the rationals. The rationals are a subset of the real numbers, and the real numbers are a subset of the complex number system. And so we can think of this as ever expanding and increasing the size of our number system. And we talked about that quite a bit in our last section. The empty set is a subset of the set of presidents of the USA. Well, that's certainly true because the empty set is a subset of every set. Pi, 2.235, and I is a subset of the real numbers. Well, pi is an element of the real numbers. 2.235 is an element of the real numbers. But I is not an element of the real numbers. It is our imaginary unit. So if we interpret I as being our imaginary unit, this is a false statement. And number 6, the set containing 1 and 3 is a subset of the set containing 5, 3, 4, and the set 1 and 5. This is false because 1 is not an element on the right side. It has 4 elements. One is 4, another is 3, another is 5, another is a set containing 1 and 5. 1 is none of those 4 things, so it is not an element of the set on the right, and yet it is an element of the set on the left. So the set on the left is not a subset of the one on the right. So it's a false statement. Alright, now what we're going to do is we're going to talk about some operations that we can perform on sets. You know, when we introduce numbers, we want to do operations on numbers, like things like add and subtract and multiply and divide. Well, we'd like to do some operations with sets. Sets are nice little objects, and we like to do things with them. So we're going to introduce 3 or 4 little operations that we can do here. The set operation intersection with this very simple upside down U, very simple U, no serifs or curly stuff, just a very simple shape there. This corresponds to the logical operator AND. So let's think about a couple of statements and the word AND. So let A be the event that you will finish viewing this slideshow today, this video today. And let B the event that you will complete the homework based on this slideshow and video today. Now consider an event C that you will finish viewing the slideshow today and you will complete the homework based on this slideshow today. The only way you can truthfully complete C, to make C true or satisfy the event C, is to complete both the events A and B. If you do A but not B, then you've made C false. If you do B but not A, you've made C false. And certainly if you don't do either one, you've made C false. The only way you can make C true is to make both A and B true. You have to satisfy both things. So in sets, this is what we call the intersection or overlap of the two events, or two sets. Okay? So we say A intersect B is by definition the set of all x, such that x is an element of A and x is an element of B. So intersection and go together. Now we can see this in an example and with something we call a Venn diagram, V-E-N-N. So this diagram in the upper right here is an example of a Venn diagram. It's named after a mathematician named Venn. And suppose we do, here's a little sort of like a probability experiment we might do, is suppose we take a fair die and roll it and see what number of dots comes up on the top. And we could have, and so we have, here we have a universal set, which is the set S of, in probability called the sample space, of all possible outcomes. It's either 1, 2, 3, 4, 5, or 6. And the event A is that we're going to roll an odd number, and B is the event we're going to roll a prime number. So the odd number, A, is the set 1, 3, and 5. Those are the possibilities for rolling an odd number. So we're going to let A be the set 1, 3, and 5. B is the set of prime numbers that are in our set S, and that's the set containing 2, 3, and 5. So that's represented, B is represented by the what's inside the red circle, 2, 3, and 5. A is represented by what's inside the green circle, 1, 3, and 5. S is what's represented inside the whole outside shape. So that includes 1, 3, 5, and 2, but also 4 and 6. And then what's A intersect B then? It's the overlap. It's where you could shade A and shade B, then the double shaded area would be the overlap or the intersection. So what's left when we're done is the purple area there that contains both 3 and 5. It's the overlap of the two. Sort of the opposite operation, in somewhat opposite, is the union. Okay, and a union corresponds to the logical operator OR. So let A be the event that you'll finish viewing the slideshow today, B the event that you'll complete the homework based on this slideshow, and D be the event that you will finish viewing the slideshow today or you will complete the homework. So D is A or B. So let's see what happens. What if you don't do A and you don't do B? Well, then certainly A or B is false. So if A is false and B is false, then A or B is false. What if you do A but you don't do B? You've finished the slideshow but you don't do the homework. Well, that would be that would make this a true statement because you said you could do A or B. Well, you did A but not B. That makes that okay. So we want to include those things. What if we go the other way around? What if we do B but not A? In other words, we complete the homework but we didn't finish watching. We did it without watching the slideshow all the way through. Okay, well that's okay too for the purposes of this OR, because if we do A or B and we do B but not A, that's fine. What if we don't do either one? Well, certainly that's going to be false. But what if we do both? We say do A or B and we do both. Then that is a true statement. So doing both things, in other words, the intersection is included here. So A union B, you see down here at the bottom, is defined to be the set of all x such that x is an element of A or x is an element of B using this logical inclusive OR. Now notice that not everyone uses OR in this way in everyday life. You tell your kid, okay, you can have cake or you can have ice cream. And the kid says, yeah, let's give them both. Well, logically speaking, that is a perfectly fine solution. Having both is a possibility. If you really want to exclude the possibility of both, what you should say, logically speaking, is you can have cake or you can have ice cream, but you cannot have both. That would be something we would call an exclusive OR, where you can't do both. Okay? Here we're talking about an inclusive OR, and this is the way it's always used in mathematics and logic or in computers. So here, using the same setup, the same sets S, A, and B, when we talk about A union B, we shade A, we shade B, and we keep all the shade. If it's shaded once, twice, if it's shaded at all, it's shaded, so it's included. So this is going to include all of A and all of B. So it's going to include 1, 2, 3, and 5. So you can think of it this way. If you want to do intersection, you have your two sets A and B. You look and find things that are in both sets. When you find a pair, you include that in your set. And you do that, look through everything, finding all the pairs, things that match up in both sets. The overlap, the intersection. But when we're doing union, we just simply take the two sets, dump them together in a new set, and that new set is the union. And again, remember the 3 and the 5 here, for example, they're not in there twice. It's just a set. Either they're in there or they're not in there. So we don't list them twice. Okay, so here's some basic true set statements for any sets A and B. A is a subset of A for any set A. The empty set is a subset of A for any A. If A is a subset of B and B is a subset of A, the only way that can happen is if A equals B. And so that's an if and only if statement. A equals B implies that A is a subset of B and B is a subset of A. And it goes the other way too, because if A is a subset of B and B is a subset of A, then A has to equal B. Alright, next statement. A is a subset of B. If that turns out to be a subset of A, well, A subset of B, A intersect B, I should say. Let me say it right. A intersect B is always a subset of A. A intersect B is a subset of A, and A intersect B is always a subset of B. A and B, in turn, are both subsets of A union B. So, of course, that makes A intersect B a subset of A union B. And if we put these things in a chain like this, here we have 3 sets. A intersect B, subset of A, which is in turn subset of A union B. This is what we call a transitive property. We can say the first one is a subset of the last one as well. If A intersect B turns out to just be A, that means A is a subset of B. Think about that a minute. If A, you see where A overlaps B, and you get all of A, that means all of A is inside of B. If A union B turns out to be A, then it turns out to be the other way around. B is inside of A. B is a subset of A. If you throw all of A and all of B together, and you get A, so adding B in doesn't add anything more than what we had to A to begin with. That means B must have already been inside of A to begin with. And a new term here, disjoint sets, means that their intersection is the empty set. So there's no overlap. If A intersect B is the empty set, then A and B are disjoint sets. That's a definition of disjoint sets. Alright, another operation is called the complement of set A in the set B. It's denoted B subtract A, looks like subtract A, or B backslash A. I kind of like the second notation better in a way because it's not truly subtraction, but really in a way it is subtraction. It's like the sort of the set version of subtraction. Union is sort of like set addition. You know, in addition, basically we just kind of put things together. That's kind of what we're doing with union. Subtraction, we're kind of taking things away, and this complement of set A and B is kind of what we're doing there. So what we're doing is, so if you have B backslash A or B minus A, what you're doing is you're taking the set B and then taking out any elements of A that are in B, taking away those. So what you're doing is really removing the intersection of A and B, and what's left over is the stuff that's in B that's not A. So this can be read as basically this is a set of elements of B that are not elements of A. So X is an element of B subtract A if and only if X is an element of B and X is not an element of A. So again, with our same sets we were looking at, where S is the set 1, 2, 3, 4, 5, 6, A is the set 1, 3, 5, B is the set 2, 3, 5, we have our Venn diagram up above, and B subtract A is the set containing 2. So think about, you start with the set B, 2, 3, and 5, and then you erase anything of A. Of course, the 1 was not there, even there, but we erase anything that was in A, so we erase the 3 and 5, and what's left is this part over here, which in this case is just the element 2. So B, the complement of A in B is 2. Now if you just talk about the complement of a set, we need to be talking about some universal set. So our universal set here again can be the set 1, 2, 3, 4, 5, 6. So it's some larger universal set. Then we can talk about the complement of A. There's actually at least 2, maybe more notations for it. Sometimes it's A superscript C or A with a bar over it. So that's the complement of A. And again, there has to be some understood universal set U. So what is the complement of A? It's the stuff that's not in A. Okay? So it's exactly what's not in A. So A and not A and the complement A, are automatically disjoint, and the two union together to give you the whole universal set. So that's basically what I've said here. So if A is the set 4 and 6, then not A would be the set, whatever's in the universe that's not in A. That would be the set 1, 2, 3, and 5. Notice if we take A intersect not A, we always get the empty set regardless of what A is. A union not A is going to be the universal set, whatever that is. And so not A is basically the universal set, take away A. So summarizing, here are the 4 basic operations we've looked at. First of all, union, A union B. We say that X is an element of A union B if and only if X is an element of A or X is an element of B. And you see we include all of A and B, including the overlap, in the union. So everything that's red down there is part of the union. The intersection, A intersect B, we say X is an element of A intersect B if and only if X is an element of A and X is an element of B. It's the overlapping part. So it's only what you see that's in both sets, the red shaded region in the Venn diagram. The complement of A is the things that are not in A. So X is an element of the complement of A if and only if X is not an element of A. But of course you have to have some universal set for this to make sense. So if the universal set is represented by this rectangle, then the red region there, it represents the complement of A. The complement of B and A, or A take away B, or A backslash B, that's X is an element of that set if and only if X is an element of A and X is not an element of B. So we started with all of A and then we erased B, and so we only get what you can see in red there, the stuff that's in A that doesn't overlap with B. Alright, let's take this now and see if we can do a few exercises here. So we're going to assume that you're given a few sets here. A is the set 1, 2, 3, 4, 8. B is the set containing 1, 3, 5, and 9. C is the set, these prime numbers, 2, 3, 5, and 7. And the universal set is the set 1, 2, 3, 4, 5, 6, 7, 8, and 9. So see if you can illustrate these sets using a Venn diagram. So draw a Venn diagram out and place all these numbers in the appropriate sets. And then use the diagram to help you find these 12 sets here. Okay? So I'm going to ask you to press pause. We'll come back and look at the next 6. Maybe press pause again and then come back and look at the end. Okay, press pause now. Okay, so let's start by doing this. We have our universal set, which we can represent by the big rectangle. And then we have our sets A, B, and C. In the general situation, for 3 sets overlapping, we can represent by 3 circles like this. So anything that's in the blue circle is inside set B. Anything in the red circle is inside set A. Anything in the yellow circle is inside set C. And we have some overlaps. And then we have one number out in the universal set that's not in any of the other sets. That's 6. So let's just go through here and look through the numbers. If you look at 1, it's in sets A and B, but not in C. And so you can see where I put it there. Okay, it's in the overlap of A and B, but it's outside of C. 2 is in A and C, but it's not in B. Okay, and you can see where I put that. That's over here where it's inside A and C, but outside the intersection of all 3. 3, however, is in the intersection of A, B, and C. It's in all 3, so it goes in this little part in the middle, where it's in all 3 sets. 4 is in A, not B, and it's not in C either, so it's in A only of the 3. So it's got to go inside of A, but it's got to go outside B and C. Same thing's true for 8. Okay, 5 is inside, not inside A, it is inside B, it is inside C. So it's in B and C, but not A. 6 is not in any of A, B, or C, so it's just out in the universe somewhere, but outside of A, B, and C. 7 is in C, but not the other 2. 8 is in A, but not the other 2. 9 is in B, but not the other 2. And that gives everything that's in the universe. So now we have a nice little Venn diagram, and we can easily answer these questions now. A intersect B is the overlap of A and B, which is 1 and 3. We can see it from our Venn diagram. We can also see it from the sets where we look and see where we find things that match up. And the only pair we match up is 1, and then also 3. B intersects C. From just by looking at without the Venn diagram, we see the 3's match and the 5's match. So it's a set containing 3 and 5, and that agrees with our Venn diagram here. B union C says you throw all of B and C together. So it's 1, 3, 5, 9. Also 2. We already have 3. We already have 5 and 7. So you can list any order you want. If you want 1, 3, 5, 9, 2, 7 would work, or I just put them in increasing order. Now over here you can see that's all of B and all of C, everything down here. So it's 1, 2, 3, 5, 7, and 9. B take away A. So we start with B, 1, 3, 5, and 9, and we erase things that are inside of A. We erase or eliminate or remove 1 and 3. What's left? Just the 5 and the 9. So it's the set containing 5 and 9. You can't just say 5, 9. You need the curly braces to make it a set. The set needs the container. Okay, A take away B, on the other hand, is different. You start with all of A and you eliminate B. So once again, we're eliminating the 1 and 3, but what's left? This time the 2, 4, and the 8. And the complement of A is the whole universe take away A. So we start with everything and we erase A. What's left? The 5, the 6, the 7, and the 9. Okay, let's look at the next one. A intersect B, and then in turn intersect that with C. If there are no parentheses, we do these operations left to right with no precedence. Not one takes precedent of order over the others. So here we should do A intersect B first, which gives us 1 and 3, and then intersect that with C, and that gives us just the set containing 3 only. If we first intersect A and B and then union it with C, so first intersect A and B, we get 1 and 3, and then we include all of C. So we're going to include all of C along with this part up here. So we're going to get the 1, 2, 3, 5, and 7. What about A intersect? Okay, so let's see. We've seen that the triple intersection is the middle here with 3. We've seen if we take A intersect B and union that with C, we get A intersect B is 1 and 3. Union that with C, we get 1, 2, 3, 5, and 7. And number 9, we want to take B union C first. That gives us 1, 2, 3, 5, 7, and 9. And we want to see where that overlaps with A, and so that's 1, 2, and 3. The set containing 1, 2, and 3. If we take A intersect B and then take its complement, so A intersect B is 1 and 3, and then we want everything but that. So that leaves us with the set containing 2, 4, 5, 6, 7, 8, and 9. Notice, by the way, that's also the complement of A union with the complement of B. If we take things that are not in A, that's 5, 6, 7, and 9, and we throw in as well the stuff that's not in B, 2, 4, and 8, you get the same thing. The only thing left out is the 1 and the 3. The complement of A intersected with the complement of B, you take the things that are not in A, that would be the 5, 6, 7, and 9, and see where that overlaps with the things that are not in B. That's the 2, 4, 6, 7, and 8. And where those overlap is just the 6 and 7. If you notice, that's the complement of A union B. So the second way to do it there is take A union B, all of A and all of B, and that's what you throw out. You keep what's left that's not in A or B, and that's 6 and 7. So the set containing 6 and 7 is what we get there. If we take A union B and then intersect that with C, we take A union B, that's all of A and B, that's 1, 2, 3, 4, 5, 8, and 9, and we see where that overlaps C, and that's the 2, 3, and the 5. So problems like this, the Venn diagram can be very useful. And notice in this Venn diagram I've actually listed the elements. Now sometimes we can take, for really big sets, instead of listing this, we might list how many elements are here. Like there's 1 here, 1, 1, 1, 1, 1, 2, 1. We could list the numbers of elements in each one. That's going to be useful for this next exercise. So here's a real-world example. During the summer, 171 students toured Europe. Among their perhaps other language skills were these skills. 46 of the students spoke German, 52 spoke French, 18 spoke Italian, 19 spoke both French and German, 6 spoke both French and Italian, 5 spoke German and Italian, and 2 spoke all 3 of these languages. So give us an illustration of this with a Venn diagram. Rather than putting each element in there, we can't because we don't even know the names of which students spoke which languages, but we can put how many students were in each of these little different pieces of our Venn diagram. So go ahead and do that, putting the sizes in the Venn diagram, and then use it to answer these questions. How many spoke French and Italian but not German? How many spoke German but neither French nor Italian? How many spoke at least 2 of the 3 languages? How many spoke only 1 of the 3 languages? And was there anybody, or how many, that spoke none of the 3 languages? Go ahead and work this out now. Press pause. Okay, now that you're back, I want to have you check something before we go on. When we say 2 spoke all 3, that includes, or the some that spoke German, the 46 that spoke German, includes the 3 that spoke all 3 languages, the 2 that spoke all 3 languages. It also includes the 5 that spoke German and Italian, and it also includes the 19 that spoke French and German. But now that 19 that spoke French and German and the 5 that spoke German and Italian, 2 of those are the same people. So we want to make sure that we're really careful that we didn't double count people. So I want you to go back and look at what you've done and make sure that you didn't count people twice. So be careful. And let me give you a hint. Start in the middle of the diagram and then kind of with the triple intersection, then go to the double intersections and then the singles, and then finally get out to figure out the last question, how many spoke none of the languages. Work your way outwards. Okay? So let me have you go back and examine what you did just a little bit more before we go on. Press pause again. Okay, now that you've done this and looked it over, maybe made some corrections, let's take a look at how we're going to do this. Well, notice that we have 2 that spoke all 3 languages. That goes here. F is for French. This is the number of students who spoke French altogether, or these numbers added together. The number German is these numbers added together, and Italian here. And the total universe, you add all of the students, all these numbers together will give you the total students on the trip. So 2 spoke all 3 languages. That goes in the middle. Now, next, let's see what we have here. 19 spoke French and German. So that's going to be this part right here is 19, but we already have 2 of them accounted for. So that leaves 17 more that spoke French and German, but not Italian. Okay, similarly, 6 spoke French and Italian. So there's 6 in this part right here for French and Italian, but we already have 2 of them. So that leaves 4, 6 minus 2 is 4, that spoke French and Italian, but not German. Similarly, we had 5 speaking German and Italian, but we already have 2 of them that also spoke French. So that leaves 3 that spoke German and Italian, but not French. So notice how we started in the center, worked our way out. Let's keep working our way out. There are 52 that spoke French. Well, we already have 4 here, 2 here, and 17. So add those together. Let's see, 17 plus 2 is 19, plus 4 is 23. And if we'll add 29 more, that will be 52 French. So add these 3 up and subtract from 52 to get the 29. If you add all these, 29 plus 4 plus 2 plus 17, we should get 52 speaking French. We add 4 and 2, we get the 6 that spoke French and Italian. We add the 2 and the 17, we get the 19 that spoke German and Italian, and of course the 2 that spoke all 3. Similarly, we can take the fact that there are 18 speaking Italian. We've already accounted for 4 plus 2 plus 3 is 9 of them, so that leaves 10 out here. And the German speakers, there are 46 of those, so that's going to leave 24 here, because we already counted for 22. 24 more will make 46. Now, if you add all these together, we see that we're 82 short of the total 171. And so there are 82 out here that spoke none of those 3 languages. Perhaps they spoke some other language, maybe English or Spanish, perhaps. So, how many of these students spoke French and Italian but not German? So we need French and Italian, not German. That's 4. So this would be F intersect I, take away G. We use our set notation. German, but not either French, but neither French nor Italian. German, but neither French nor Italian. So this would be G, take away F, and take away I. So G, take away the French, take away the Italian. What are you left with? These 24 here. How many did at least 2? Well, that's these 4, these 17, these 3 did exactly 2 of these 3 languages, but this one also did at least 2. So add the 4, the 2, the 17, and the 3 together. That's 26 students. How many only spoke 1? Well, that would be these 10, these 29, and these 24 added together. 63 students. And how many spoke none? 82. Now we're going to go on and talk about interval notation. Interval notation is a notation used for writing down what we call intervals of real numbers. So this is something, when we have an interval, it's automatically a subset of the real numbers, but they're going to be nice connected subsets. So an open interval, written as parentheses A, open parentheses A, comma B, close parentheses, that's interval notation. Set builder notation for the same thing would be the set of all x such that A is less than x, which in turn is less than B. And so our graphic notation is, notice that the A and the B are not included, so we use these open points, open circles, to represent the fact that A and B are not included, but we shade everything between A and B. So this is everything between A and B, but not A and not B. Okay? And all these notations, A is on the left, B is on the right. So you can see that shaded on the number line. Okay? A closed interval would be an interval that's the same as the open interval, but it also includes the endpoints. And we include the endpoints if we have this square bracket, and we do not include the endpoints if we have the open round parentheses. So bracket A, comma B, bracket is interval notation, and set builder notation for the same thing would be the set of all x such that A is less than or equal to x, which is less than or equal to B. And so notice this is an actual closed line segment from A to B. The open interval is an open line segment. It's a line segment with its endpoints removed. Now you can have half open and half closed intervals. I'll call this next one closed open. Closed on the left, open on the right. So bracket A, comma B, parentheses, that's the set of all x such that A is less than or equal to x, which is strictly less than B. Notice that we have a solid endpoint on the left and an open endpoint on the right. So notice this interval has no largest value. No matter what value you tell me, I can find you a value larger than that that's closer a little bit to the right of whatever you tell me is in the set, but still less than B. But it does have a smallest one, which is A. Then we can have an open closed, which is parentheses A, comma B, bracket, which is a set of all x such that A is less than x, which is less than or equal to B. This time it's just you close in the one on the right, you open the one on the left. Now some people will graph these and they'll actually use, where I'm using a dot, they'll actually use the little bracket symbol, and where I'm using the open circle, they'll use the parentheses symbol. This is actually better the way I do it because we're actually talking about an actual point on there. And just as in geometry, when we graph a point, we put a little dot for it. And so this is much better, and particularly translates better to two-dimensional graphs and so forth. So I want to use this version here. But if you ever see another version, you'll understand how the connection with the interval notation if you see it. Now we can have unbounded intervals. Uh-oh, I got these backwards on the graphs. Graphs got jumbled out of order a little bit here. I'll fix that for the printout. This is the open interval from A to infinity. Parentheses A, comma infinity. It's a set of all x such that A is less than x. Or in other words, x is greater than A. And we go down here, it should have an open endpoint at A and go to the right forever. So this one right here is the one that matches this one. These two should be matched up here. This is a closed interval from A to infinity. It's a set of all x such that A is less than or equal to x. In other words, the set of all x such that x is greater than or equal to A. This includes the A and then goes to the right. So this one with the solid endpoint should go with that one. Then we can have open intervals, or intervals going to the left. Okay, so parentheses negative infinity to B, parentheses, that's the set of all x such that x is less than B. And so this infinity is on the right, saying that there is no right, really. It just goes on forever to the right. And the negative infinity, when you see that on the left, means the graph will have an arrow to the left. It goes on forever to the left without, there is no lower bound. There is no lowest one. It goes on forever, okay, without bound. Okay. Similarly, parentheses negative infinity B, close bracket, is a set of all x such that x is less than or equal to B. It'll go from forever left up to and including B. If you write minus infinity to infinity with parentheses, that's another way of writing the entire set of real numbers, so everything is graphed. Now, here's a couple of examples that are not intervals, but I want to put them on here to compare and contrast. If you have the curly braces with A and B, that's just the 2 points A and B, not anything in between. So curly braces AB, or BA, is just the 2 dots A and B, the single 2 points. All of these intervals, like the parentheses AB, that's the interval, the numbers between A and B, not including the A and the B, but includes infinitely many numbers of real numbers that are between. Bracket A, comma B, bracket, that is a closed interval. That's all the numbers between A and B and the interpoints A and B as well. And of course the empty set, nothing's graphed. I'll fix this one matchup before you get it for the printout. Note that the square bracket, left or right, indicates that the endpoint is included, while the round parentheses, left or right, indicates that the interval does not include the endpoint. Now, if you have AB, A comma B with parentheses or brackets, or those half ones, any combination of parentheses and brackets, they imply that A is less than B. So intervals always must be listed from left to right on a number line. In other words, from a smaller number to a larger number, or from the number on the left is less than the number on the right. So the interval 3 to 5, open on the left, closed on the right, is allowed, but 5 to 3 is not allowed, because that says that 5 is less than 3, which is not true. It's not possible. So this first one makes sense. This second one, it doesn't even make sense at all, so it's not allowed. Intervals turn out to be connected sets of real numbers. Graphically, a single interval is one connected piece. It's either a line segment with or without the endpoints, or it might be an array with or without the endpoints, or in the case of negative infinity to infinity, it's the entire line. So they're basically parts of a line that are one connected piece. Now this symbol that we use for infinity, kind of like a sideways 8, represents positive infinity, and if we put a negative in front of it, it's negative infinity. And these are not real numbers. Okay, so they're not part of the real number line. They're not part of the set of real numbers. They're never included. Since they're not real numbers, you'll never have a closed bracket on positive or negative infinity. You'll always have a parentheses there because they're not included, because they're not real numbers. Okay, because we're talking about intervals as intervals of real numbers. We cannot include infinity as a real number because this is not one. Now, if we have an infinity sign present, a positive infinity sign, it's always got to be on the right of the interval because it's always bigger than any real number. It's always out to the right. So this means it goes to the right forever. And similarly, negative infinity, if it appears, has to be on the left side of your interval because it means it's forever left. Now we do have an unfortunate thing here. If you see something parentheses A comma B parentheses, it could represent an ordered pair AB, which is graphically a single point in a plane. However, it could also represent an interval of real numbers, okay, not ordered pairs, but a single number, but not just a single number, a whole interval of them. That's all on one one-dimensional line. So it could be only things that are on a line, but a whole infinitely many of them in an interval, or it could be things that are in a plane, but only one single point. And we use exactly the same notation for that. So you're going to have to know from the context which one it's talking about. Unfortunately, it's the same notation. All right. If you see these things, which ones of these could be intervals and which ones cannot be intervals? And if they're not going to be intervals, what's wrong with the notation? What is it that make them not be intervals? So take a few seconds, work this out, and then come back. Press pause now. Okay. Well, 3, 6 is an interval. That makes sense. That's an open interval. It's the numbers between 3 and 6 on the number line. Does not include 3 and 6. 3, 7 is also good. That's the set of numbers between 3 and 7, including the 3 and 7 as well. That's a closed interval. 7, 2 is not an interval because if it was an interval, it would say 7 is less than 2. Well, that's not true. 7 is greater than 2, so that one's not allowed as an interval. If you saw that, either you messed up and wrote something wrong, maybe you meant to write 2, 7, or perhaps you were talking about an ordered pair, and it would be allowable for that. Number 4 is not allowable for an interval because we have a square bracket saying we're including negative infinity. Negative infinity is not a real number. We cannot include it. Probably we meant to put a parenthesis there on the left. Negative 5 to infinity is totally fine. That's the numbers that are greater than negative 5. Not including negative 5, just everything to the right of negative 5. Infinity negative 2 is not an interval because you can't have infinity, positive infinity, on the left. I'm not sure what this, you might have made a mistake here and it might have meant negative infinity to negative 2, or you might have meant negative 2 to positive infinity. Those things would have made sense. Negative infinity to negative 2 would be the numbers that are less than negative 2. Negative 2 to infinity would make sense. That's the numbers that are greater than infinity. But infinity to negative 2 doesn't make sense. That's not allowed. The set 3, 6 is not an interval. It's a totally legitimate set of points, but it's only got 2 points, just the 3 and the 6. Nothing in between. Negative 3, negative 5 is not an interval. It's just like the 7, 2. They're in the wrong order. You need to have, if you mean the numbers between negative 5 and negative 3, you have to list the lowest number first. You have to go negative 5, comma, negative 3. So that's not allowed. 4, technically maybe you could call that an interval, but it really degenerates because it really just means the one single point, 4, and it'd be much better to write it as the set 4 because that's all you really have. The numbers between 4 and 4 include 4 is 4. So not really an interval anymore, it's just one single thing, even though it's not completely undefined. So we want to write these in interval notation. The first 5 I've given it to you in set builder notation and ask you to write it in interval notation. And 6 through 10 I've given you the graph and you have to write it in interval notation. So let's give you a chance to work these out now. Press pause now. Okay, now hopefully you're doing these exercises as we say them. If you make some mistakes, that's fine, but you'll learn from your mistakes. If you're getting them right, then you're going to feel great when we check them here. So the numbers that are less than 5, that goes from negative infinity up to 5 and does not include 5, so it's parentheses, negative infinity, comma, 5, parentheses. The set of all x such that 3 is less than x, which is less than 7, this is the kind of thing that intervals are just perfect for. Parentheses 3, comma 7, parentheses, a much more compact way of writing that than the set builder notation. The next one, when we see 3 is less than x is less than 7, that's a shorthand for writing 3 is less than x and x is less than 7, which is kind of the way I wrote the next one. The set of all x such that 4 is less than x and x is less than 6, that's the numbers between 4 and 6, so that's parentheses 4, comma 6, parentheses. Now this next one is not an interval, it's actually 2 different intervals unioned together. So the set of all x such that x is less than negative 3 or x is greater than 5, remember or relates to union, so we're going to need a union here. X is less than negative 3 is from negative infinity up to negative 3, so it's parentheses negative 3 comma parentheses negative infinity comma negative 3 close parentheses. We're going to union that with parentheses 5 comma infinity close parentheses. So this case the interval notation is a little bit more cumbersome because the answer's not really one interval, it's 2 separate intervals, kind of like number 10 down here. The graph would be in 2 parts. And number 5, the set of all x such that the absolute value of x is less than 3. These are the things that will be close to 0. How close? Well, between negative 3 and 3. So that's parentheses negative 3, comma 3, parentheses. Okay, look at number 6. I know these numbers are a little bit small, but hopefully you can see these. Right here in the middle in red is the coordinate 0, and all of them are exactly the same scale. Then each dot goes up 1, 2, 3, 4, 5, and so forth. So if you'll see, this is 3, and this endpoint is 6, 3, 4, 5, 6. A little small to see there, but that's 6 and that's 3. And so it's everything between 3 and 6, but if you see, you have open endpoints at the end, so it is parentheses 3, comma 6, parentheses. Okay, then let's count here. 0, 1, 2, 3, 4, 5. So that's 5, 6, 7, 8. So that's between 5 and 8. And this one has solid endpoints, so we include 5 and 8. So it's bracket 5, comma 8, bracket. This one here starts at -2 and goes up to 3. So notice how I'm always reading these left to right on the number line. So -2 to 3. We don't include the -1, we do include the 3. So that's parentheses -2, comma 3, bracket. This one starts at forever left, so it starts at -infinity. That's parentheses -infinity, comma, and it goes up to and includes 3. So 3, bracket. Now this next one is not one interval, it's in two pieces, very much like number 4 up there. So the first piece goes from -infinity up to -2, but doesn't include it. So it's parentheses -infinity, comma -2, close or open there, close parentheses, union with this other part over here, which starts at 4 and goes to infinity, but doesn't include the 4. So parentheses 4, comma infinity, close parentheses. Okay, this time we're going to go the other way around. This time, instead of me giving you the graph and you tell me the intervals, this time I'm going to give you the intervals, or the sets, and you're going to graph them on a number line. And actually, if you're a little careful, you can probably set up your number line, looks like going from about, say -4 to 10 would be fine. And get you a piece of graph paper out to do this. It's my suggestion. Mark it off evenly from at least from -4 to 10, one mark for each thing, and we could just do a whole bunch of number lines, horizontal number lines, 1, 2, 3, 4, 5, 6, 7, 8 number lines, and use the same scale all the way up and down, and then graph these. Go ahead and do that now. Press pause now. Okay, so if we set this up with a graph paper, that will indicate that'll set us up so that we are sure that we're exactly even on our scale. And this turns out to be what we have here. So I actually have this number line running from -10 to 10, and I've got these graphed. So the open interval 3 to 5 should start at 3 and go to 5. It's all the stuff between 3 and 5 that you see graphed in blue here. So I got my maybe get some thick colored pencils and graph over there so you can see it. But notice that we put a round dot at both 3 and 5 because we do not include the 3 and the 5. The next one's the interval from 4 to 7, so we go between 4 and 7 and shade those. Here I shaded red, but we put a big red dot at 4 and at 7, a solid dot, because we do include those. The next one goes over here from -2 to 9, but we don't include the -2, we do include the 9, and then we include the stuff in the middle that's green there. The next one's closed on the left and open on the right from 3 to 6. So a dot at 3, open dot at 6, and shade in between, the purple. The next one with these curly braces is not an interval at all. It's just the two numbers 4 and 8. So we got a big red dot here at 4, big red dot at 8, nothing else, just 2 points. The next one, 3 to infinity, we put an open circle at 3, open dot because 3 is not included, and we shade everything to the right, including shading in a big arrow there, say that all these things forever to the right are included. The next one also goes to the right forever, but starts at 4 and includes 4, so a solid dot there and goes on to the right. And the last one goes from forever left, solid arrow to the left, and goes up to, but not including, a point at 5. Okay, so now we're going to use graphs on a number line to help us sort of combine a couple of things that we've been doing in this unit, or in this particular lecture, where we're talking about graphing sets of points, whether they're lists or whether they're intervals, and graph that on a number line. But then we're also going to talk about taking these sets and doing some things like unions and intersections and complements. So here, the first thing I want you to do, again, is get out a piece of graph paper, and you can probably, again, go from like, well, -4 to 10 will work fine, or -10 to 10 like I used. That'll be fine. And then, once you have that, make a line for each one. You're going to make a line for A, then below that, on the next line on your grid, you're going to make a number line for B, and then a number line for C, and a number line for E. So you're going to have 4 different things there. And then we're going to have lines for 1, 2, 3, 4, and 5 down below. So graph A, which is a set 1, 2, 3, 4, and 5. Set B, which is the open interval from 3 to 8. Set C, which is the closed interval from -1 to 5. And set E is the set of even integers that you're going to graph here. And you might get some nice colored pencils out. Get a different colored pencil for each one of those 4. Okay? Make use of those colored pencils I asked you to buy. And then go down here and graph these 5 here. So go ahead and do this out on your graph paper, and then come back and we'll check these in a few minutes. Press pause now. Okay, now we're back. Let's take a look here and see if you came up with this. So I chose here to set my graphs up going from -4 to 10 on the number line. The number line, of course, goes on forever. Excuse me. So here, let's take a look at this. So A is a set 1, 2, 3, 4, 5. So that's just 5 dots, which are given by the green dots here. Dots at 1, 2, 3, 4, and 5 on our number line. Notice I've lined all these number lines up just like I would if it's on a big piece of graph paper. And B is the set from 3 to 8, the interval from 3 to 8 that's open, so we do not include the 3 and the 8, but we include what's in between. That's graphed in blue. And in red we see interval C, which is the closed interval from 1 to 5. So this one includes 1 and 5 and everything in between. And E is the set of even integers, which goes on forever, but the ones that are on sort of in the window here I have graphed are -4, -2, 0, 2, 4, 6, 8, and 10. And of course it does go on forever. I should have probably indicated that somehow, but okay. Now, what is A intersect B? The overlap of A and B. Now, we can see this pretty nicely just by looking at the 2 graphs. By lining them up carefully like we did here, that's part of why I want you to get the graph paper out, we can see where these 2 things line up. So first of all, it's got to be part of A, so it's got to be 1, 2, 3, 4, 5 at most. And then we got to see where that overlaps this blue. So where do the blue and green overlap? Well, the 1's not in the blue, the 2's not in the blue, the 3's not in the blue because the blue interval B does not include the endpoint 3. But the 4 and the 5 are. The stuff between 4 and 5 and the stuff out here like 6 and 7, those are not included because they're not in A. So we end up with just 2 points, the set 4 and 5, and so we get those 2 dots, which I've graphed in pink down here. Okay, we want to do the overlap or intersection of B and C. Now, let's see what we got here. Well, this part over here gets erased, and this part over here gets erased. What gets kept? Well, 3 does not get kept because it's not in the blue interval B, but it is our boundary. So there's an open dot at 3. We do, however, include this solid point at 5 because 5 is in both the blue and the green. It's in both intervals. So we have a solid endpoint there, and the stuff in between 3 and 5 is included. So it's open on the left and closed on the right, the interval from 3 to 5. And of course I've asked you here to actually write down the interval notation for it, or if it's just a few points, just list it as a list with the braces. And so we can work this out and we see that. Okay, what about B union C? We shade all of B, which is the blue, and then we shade all the C. Some get shaded twice, like the 3 only gets shaded once, the stuff between 3 and 5 itself gets shaded twice, but as long as it gets shaded at least once, it's good. So ultimately we get everything from -1 up to 8, but we don't include the 8, but we do include the negative 1. The negative 1's included here. The 8's not included in either one. So we get negative 1 closed up to 8 open, so that's bracket negative 1 comma 8 parentheses. So it's closed on the left, open on the right. C intersected with E, the even numbers that are in C. So C's this here, and we want the even numbers. Let's see. So we're looking at the pink and the red here where they overlap. So this one's an overlap, this one's an overlap, and this one. And that's 0, 2, and 4. And that's all we get is those 3 dots, 0, 2, and 4. I graphed them down here in red. And then if we do A, take away B. So we start with A, these 5 dots, and we erase anything that's in the blue. So we start erasing across here, and we end up erasing that dot, that dot. We don't erase that dot because it's not part of B. So we end up keeping the 1, 2, and the 3, and so we end up with just 3 dots on our graph. So hopefully Venn diagrams can be very helpful for seeing sets and unions and intersections. If the sets are sets of real numbers, then graphs on a number line are very useful for keeping track of things. And if you put these number lines together with the same scale, they can be very helpful in helping you understand intersections, unions, complements, and so forth. So we're about to the end of this one here. Let's review the kinds of things that we should be able to do after finishing this particular section here. So after studying the material in this presentation, students should be able to understand and use standard notations for sets, including bracketed list, or I should say list and braces, set builder notation, interval notation, and symbols for standard sets of numbers such as in natural numbers, whole numbers, integers, and so forth. Students should be able to demonstrate a mastery of basic set concepts, notations, and properties, including things like the empty set, element of, subset. We also talked about the power set. They should be able to perform operations on sets using appropriate notation. Things like intersections, unions, complements, set subtraction basically, which is also really complement. And they should be able to utilize Venn diagrams to represent relationships among sets. Should be able to graph sets of real numbers on a number line, including intervals. And should be able to understand interval notation. Okay. That should wrap us up for this unit, or not for the unit, but for the section, and you should be ready to go on to start working on some homework. Enjoy.